So Ramin asked me to talk about capillary flow, and there's, these different layers of capillaries in the eye. I just only have 10 minutes to talk. So I thought I would talk about choriocapillaris flow, and these are my disclosures. To first talk about choriocapillaris, I just want to talk about how we measure things. The tallest guy who ever lived, whoever was recorded that we know about, was 2.72 meters, and the shortest one was 0.57 meters. So that's a ratio of only 4.8 to 1. And we know that height, if we measure lots of people, forms a sort of Gaussian curve. And it has characteristics that we expect. 1 standard deviation, 2 standard deviations, like 2 standard deviations encompasses about 95% of the people involved. If we take a sampling from just a normal population, at random sample, we would end up getting a smaller sort of Gaussian curve, and we can make estimates of the original population from that. And that's really the basis of a lot of statistics in medicine. If we look at the population of cities in the United States, the population of New York is 8 million people, and on the other end of the spectrum, there's Buford, Wyoming, population 1. So that's a ratio of 8 million to 1. That's a lot different than a relationship that we saw among height of people. Now, in reality, a lot of cities aren't that small. Most cities are 50 or 100 people, maybe at the smallest, because you have to have a mayor and a garbage collector and a policeman and all that sort of thing. But the curve that, if you plot of population versus number, ends up looking like that. And you may be familiar with that curve, maybe not. If you're not, just kind of remember the shape of that curve. If we go back to looking at populations of cities in the United States and calculate a mean and standard deviation, we get something that looks like this. The mean is about 24,000, standard deviation 50,000. So if we plot that out on a curve, expecting it to look like a Gaussian curve, remember the Gaussian curve has 95% or so of the people within 2 standard deviations, we would calculate that 2 standard deviations for the population of cities in the United States would be minus 76,000 to a plus 124,000. So you say, how can you get a population of minus 76,000? In addition, New York City would be 160 standard deviations above the mean, which means that New York City would be statistically impossible. So it's clearly we're making a mistake trying to force in non-Gaussian distributions into a Gaussian kind of idea. A guy who was important in figuring out these ideas he had a stately name, George Kingsley Zipf. And you would think he's English, but he was actually from the Midwest. And he was a lecturer at Harvard University. And he did a funny kind of study a long time ago where he noticed he counted a number of words and how often they were used. And the most common word in English language is used twice as often as the second most common word in English language. And the most common word is used 3 times more often than the third most common word. And the 10th most common word is used 10 times more often than the 100th most commonly used word. And if you plot that out, it makes a curve that looks like that. The interesting thing is if you take a log-log plot, it makes a perfectly straight line. So you would say, well, this is maybe something inherent in the English language that has this funny relationship among how often words are used. But actually, here's a plot of 30 different Wikipedias, different languages, and they all form that same straight line plot. And you can see it's a straight line plot over 12 log units. And this has been called Zipf's law. And it defines a sort of relationship when you look at a log-log sort of relationship that defines what's called a power law relationship. So power law exists definitely for languages and humans. You say, well, that's just humans. Here is looking at dolphin vocalizations. Now, for whatever reason, they're called whistles, even though it sounds like, that kind of sound they make. They make different sounds, and people have actually looked at those sounds, and young dolphins don't know too many of them when they talk to each other, but the ones they know, they use in a power law relationship, and as they get older, they learn more of them, and they use those in a power law relationship too. So this kind of curve has what's called scale invariance, and if we were like a little ant on one part of the curve, we wouldn't know the difference if we were on the small end or the big end, because its scale doesn't really change over different units of scale. And this was very interesting to this guy Mandelbrot, and he wrote his PhD dissertation about Zipf's law. And he noticed that, say, the price of cotton had different variations, and it didn't matter if you're looking at the price of cotton over 5 minutes, over a week, over 3 months, it still had these same kind of variations. And there was lots of small movements, less of bigger movements, and giant moves were very uncommon. But if you plotted them out on a log-log scale, they came out to be a straight line. He also noticed that this line was kind of invariable, again, over units of scale. And you couldn't say it was a one-dimensional line, but then on the other hand, you couldn't say it was 2 dimensions either. It had a fractional dimension somewhere between 1 and 2 dimensions, and that's where he coined the term fractal, was from looking at this. Purbach was a mathematician in the 80s who looked at how grains of sand fell down, and he made a little model that had grains of sand falling down, and they would make an avalanche when they reached certain conditions. So he recorded how many avalanches there were according to what size these avalanches had, and curiously enough, they formed a straight line on a log-log plot. So they followed a power law curve as well. And they went out and looked at real avalanches, and real avalanches, here's a shown of graph shown of log of avalanche size versus the number, forms a perfectly straight line. Power law relationship. Here's a power law relationship demonstrated for earthquakes, and you can see it exists over many log units of scale. Here's wars. They exist on a power law scale too. You notice that banking crises and corporate bankruptcies, as they occur, follow a power law pattern. People looked at volcanoes, solar flares, forest fires, traffic jams. All of these follow a power law kind of characteristic. So the way the universe works seems to be a lot towards this power law thing. Maybe in biological systems we're trapped into a little range, but the way things happen seem to be related to power laws. Here's a chorea capillaris, and you notice a meshwork of finely spaced blood vessels. And there's veins and arteries that lead into this chorea capillaris mesh, and that sets up pressure gradients that lead to a lobular flow pattern, as demonstrated to us by Hayray. Here's a 28-year-old examined with OCT angiography, and you notice that she has very small areas of flow voids. These are smaller than a chorea capillaris lobule, but it's kind of strange. Why would a 28-year-old have these present? So we did a study on flow voids inside people. Here's an older gentleman who has pseudodrusen, lots of flow voids. You can count how many flow voids there are versus their size, and look at that curve. Right? You've come to realize what that curve represents, and when plotted on a log-log graph, forms a straight line. The flow voids in your chorea capillaris form this kind of power law relationship. Now, he follows this curve that you kind of would expect, that the log of y equals some constant times the variable, the log of the x variable plus an offset. That kind of is that y equals mx plus b formula that we learned in high school. And the curious thing is that the slope is statistically related to age and hypertension. And then the offset is related to age if you have late AMD in the fellow eye, or if you have hypertension. And finally, people with big sort of areas of flow voids are more likely to be older age, have pseudodrusen, or have late AMD in their fellow eye. This kind of flow problem, or abnormalities in flow, or power law relationship in flow, has been thought to occur in tissue based on microbeads and tracer washouts, but nobody could actually demonstrate it in tissue until we thought looking in the chorea capillaris. Well, how can this occur? Well, we know first off that small segments of the chorea capillaris close down with age. And this starts, Rob Mullins showed, this starts at around age 5. And these build up and occur more and more with increasing age. You can imagine if you had an occlusion that you would have a decrease in flow around it. Much like if we block traffic, we would end up having traffic jams extend in roads around that. To build up a power law relationship, you only need a simple thing, is that you have to have more to develop over time, which we showed, and they have to happen kind of close to some other one, so it blocks off the area of flow over a bigger area. Once you set that in stage, you can set up a power law relationship, and this could be modeled mathematically, as I show here, which is to illustrate how these flow voids can increase over time. Note that if we stop this and look at different time periods, that it makes a power law relationship in each one of those time periods, and each one of those pictures emulates different age groups inside people. So there's sublobular flow alterations that are very, very common in people. They happen pretty much in all of us. We're almost programmed to have them, and they're related to systemic and ocular factors. Now, these chorea capillaris flow problems could be related to diseases. It's easy to imagine how this somehow could be related to age-related macular degeneration or myopic degeneration or any other number of diseases. And the interesting thing is they happen a kind of mathematical certainty, and we can model these mathematically. So it may be possible that we're going to be able to look at people and look at their health and systemic disease and kinds of conditions from their chordae capillaris, but also estimate their probability of going on to have late AMD. Thank you very much.
Thank you very much, Rick. Very interesting. Do you think that the drug or whatever patient take could have a direct and immediate effects on the measurements that you did here?
There's a certain statistical nature to these measurements, and could be, if you had low blood pressure, maybe we'd see different kind of flow voids, but in aggregate over time, they would be, I think, fairly constant from one person from one time to the next over a short interval.
Thank you very much, Rick.